Assalamu alaikum everyone. So today we will be having lecture number 28 and we will be discussing timing analysis, right? So these are the bullets which we will be going through one by one. First we will discuss that how circuits respond whenever we apply input, and normally what happens when we apply input, the circuitry or the digital system, it did not respond uh, instantaneously, right? We have to wait in order to see the effect of input at the output, right? So it means there is a delay, right, while the input transfers to the output, right? And that delay we normally call it propagation delay, right? This is regarding the combinational circuitry, right? Whenever we talk about sequential circuitry, right, so we all know that in case of sequential clocked sequential circuitry, right, the timing of the clock is very important, right? And our goal is to determine the maximum clock frequency we need in order to handle the circuitry or the functionality of this circuitry in a good way, right? So these are the few main points which we will be discussing in today's lecture, right? So let's talk about sequential circuit timing, right? So two characteristics are very important whenever we talk about the sequential circuitry. First, you normally have listened or seen gigahertz, megahertz, right? Whenever you go to the market and you want to buy a processor, so you are very conscious regarding the frequency or speed, right? Speed of the processor, right? So that gigahertz or megahertz, they are actually representing the clock frequency, right? And on the other hand, whenever we go to the market to buy a computer or to buy a laptop or a tablet, we are very conscious about the memory, right? So you always wish to have a more memory, right? So these are the two important characteristics regarding the sequential circuitry, right? So in case of the memory, it actually is the main memory, right? So it includes the number of storage bits, right, in a computer, in a laptop, or in a tablet, right? So here you can see in the figure we have clock, that is a periodic signal, right? And that will continue like this forever, right? Whenever we switch on the computer, right? So here, if I want to talk about the period, right? So this is the period, right? So here you can see that we have the rising edge, falling edge, and again when the rising edge will repeat itself, right? So we will mark that, all right, 2 points, and the distance between these 2 points is the period, right? So that is the period of the clock signal, right? Okay, so then whenever you think about the clock, it determines, right, that whenever the flip-flops have to function, right? So you know that if we have the clocked flip-flops, right, and the flip-flops, they are edge triggered, not the level triggered, right? So we need to have a very close eye on the possibility of the triggering, right? So if we have a positive edge triggered clock, right, so on the arrival of the positive edge, the flip-flop will function by looking at the input, right? It will behave accordingly. If we have a negative edge triggered flip-flop, right, so on the arrival of the negative edge, the flip-flop will behave accordingly by looking at the input which is applied, right? So here our goals are that minimum clock period which we discussed in the last slide. So this is the period, right? Clock period. And you know that they are inverse to each other, right? So if you have the clock period, right, so we can calculate or compute the frequency, right? So that is T minimum is equal to 1 by f, or on the other side you can say f maximum is equal to 1 by T minimum, right? So this is the goal, right? So you can see here we have defined the clock period, the time, right, between rising clock edge, right, two rising clock edges, right, is called the clock period, as we have discussed before. So this is the rising edge, right, and this is the rising edge. So you can say this is the clock period. On the other side, if you want to mention the negative, right, or the falling edge, because this is the rising edge, so let me use the pen, right? So this is the rising edge, right, and this is the falling edge. Here again we have rising edge, and this is the falling edge. Rising, falling, right, rising and falling edge, right? So here we have measured the clock period while taking into account rising edges, right? So we can do so by taking into account falling edges, right? So this will be the time between two falling edges, right? So we can say that this is the T minimum, right? Or you can also call it, right? Right? So rather we should say TPER, right? Time period. So here we have mentioned in case of falling edges or negative clock edges, right? So as we all know that whenever we have the digital logic design, we cannot escape combinational circuitry, right? So when we are designing a digital logic design, right, so we have two sort of different logics that are being involved. First one is the combinational logic, and the second one is the sequential logic, right? So if we have a circuit, a digital circuit that has both the combinational circuitry and the sequential circuitry, then we must have the timing analysis, right, on the basis of combinational logic and the sequential logic, right? So let's talk about the timing parameters that are involved in the combinational logic, right? First one is the propagation delay, right? So as I've mentioned, whenever we apply input at some of the combinational circuitry, we are not going to receive the output instantaneously. We have to wait for some time. At that waiting time is normally called the propagation delay, right? So you can take it the time the input takes in order to propagate from input to the output is called the propagation delay, right? So on the other hand, we have another sort of parameter that is involved whenever we talk about the timing analysis of combinational logic, right? So that is contamination delay, right? So that indicates the amount of time needed to change in a logic input to result in an initial change at the output, right? So this is the time when you start observing the change at the output, right? So when you have changed the input, how we define, right? So here let's talk about an inverter, right? So that is a combinational logic, basic building block of the combinational logic, right? So here we have the input, and here y is representing the output. So this is the combinational contaminational delay, right, CD, right, and this is the PD, right? So you can see that propagation delay also includes TCD, right? If So here you can see that we have the input, right? So when the output start responding, right, to the input, right, so here it should be low, right, because we have 1 here, right? So as it is an inverter, so it should go to 0, right? So here again you can see that input is 1, but the output is not going to be 1, right, till TCD, that is contaminational delay, right? So that X, first X represents, right, this behavior, right? So you can see that there are a lot of different axes, right? So here you can see that now we are having the change in the output, right, because it has to go to 0, right? So still it is taking time, right? So if I mark this, right, let me use this pencil, right? So you can see that if I mark this, so this is another, right? So here we have taken another time, right? So let me call this as TCD plus this amount of time, that is T1, that is equal to TPD, right? So we have drawn here different axis, right? So this is first X and this is another X, right? So on the other side, right, here we have 0, right? So it is 1 till here, and here we have 0, right? So again you can see it should be 1, right? But for this amount of time the output is not started changing, right? So here after TCD, contaminational delay, the output will start changing. So right, so that's what we have defined, that amount of time needed for a change in a logic input to result in an initial change, right? So that is the initial change, right? You can say that is the initial change, right? And then now from here to here you can see we have another amount of time, and that time include plus this time is the TPD, that is the propagational delay, right? So here we can see 0, it should be 1, and it should be 1 after TPD, that is the propagation delay, right? So again this is sort of more explanation regarding the inverter, right? Because we normally construct those different logics and or not from electronic components, right? So these delays are the effect of those different components, right? So this is almost the same, the output remains unchanged for a time period equal to the contaminational delay, right? So here this is something new, right? So whenever we apply a new input, right, so you are expecting the new output, right? So as a result of those different delays, contamination delay and propagation delay, right, so the output value has to be valid after a time period equal to propagation delay, and you can see that this is the output, right? So here you can see that it has to be valid after a time period TPD, right? So you can see change in input, right? We are expecting the new output, right? But it has to be valid, or you can say it will attain the previous state, right, for a time period of TPD, right? Okay, so again here as we know that whenever we talk about the digital circuitry, so we have a lot of different gates that includes and or not, that are the basic building blocks of the digital design, right? So if we have an inverter, right, and then we have an AND gate and OR gate, right? So for example, if we have a circuitry like this is an inverter, right, and then we have another AND gate, right, and then we have another OR gate, right? So how you will analyze the timing behavior in case of that circuitry, right? So far we have discussed two timing parameters, propagation delay and contamination delay, right? So when we talk about the propagation delay, that is additive, right? So what we need to do, we will be looking for the different paths, right? So here you can see that this is one path and this is another path, right? So what we need to do, we need to add the propagation delay, right? So here is an example, right? So we have a NOR gate, right, with two inputs, right, and this is the output. So you can see two inputs and output, and here we have mentioned contaminational delay, propagation delay, right? So here the output will remain stable, right, with the previous value or the old value, right, until the contamination delay. So you can see from here, right? So the change has started here, right? So this is the time, which is TCD, right? Right. So here is the example, right? So here we have more than one gate, right? So we have an inverter, and here these are the parameters, timing parameters. This is TPD, propagational delay, and this is CD, contamination delay, 2 nanosecond and 1 nanosecond, right? For this NOR, we have two more values, TPD, that represents the propagational delay, and that is equal to 3 nanosecond, and here we have the contaminational delay, and that is equal to 1 nanosecond, right? So if I draw a box, right, representing this circuitry, right, so I name it a circuit X with two inputs and one output, right? So and I have to calculate the total propagation delay and total contamination delay, right? So here you can see that we have, in case of TPD, right, we have added those values, right? So 2 plus 3 is equal to 5, so that represents the TPD, and we have mentioned before that TPD is additive, right, because we have to add it, right? Or in other words, you can say that we will be looking for the longest path when we talk about the propagational delay, right? On the other side, in case of contaminational delay, right, so we will be having the 1 nanosecond, right? Why? Because here there is no addition, it is not additive, right? It may be additive, but here in this case it is not additive. And on the in other words, you can say that in case of contaminational delay, we will be looking for the shortest path, right? For propagational delay, we will be looking for the longest path, right? And for contaminational delay, we will be looking for the shortest path, right? So here these are the same, additive, right? It may be additive, right, but most of the cases it may not be additives, right? Okay, so here we have another example, right? So it's a more complicated circuit. Here we have two inputs, right? And in this example we have three inputs, right? And the number of gates are 3, and here we have 2 number of gates, right? So you can see that we have A, right, gate A, right? So it must have those parameters in order to have the timing analysis, right? TCD, contamination delay, 2 nanosecond, and PD, propagation delay 3 nanosecond, right? So for this inverter that is named C, we have TCD, contamination delay 1 nanosecond, right? And PD 2 nanosecond, right? So here again, this is the OR gate. We have two values, two parameters, CD, contamination delay 1 nanosecond, and PD 2 nanosecond, and this is the output, right? So what we have to do, right? So we have WXY, right? So if I have to write the output, right? So how I will be writing, Z is a function of W, X and Y, right? And now I have to calculate the propagation delay, right, and the contamination delay, right? So you can see that we have two paths. First is this, right, and the second is this, right? So you can see how we will be evaluating the propagation delay, right? So if I add, because we have mentioned and we that in case of PD, TPD, it is additive, right? We have to add. So here 3 plus 2, this is 5, right? So here 2 plus 2, if I talk about this part, right? So here we have TPD 3 plus 2, 5 nanoseconds, right? So if I talk about this part, right, so then I have TPD 2 plus 2 is equal to 4 nanoseconds, right? So what I will be doing, right, so we have obey the main principle that the propagation delays are additive, right? But what we need to do, we need to take the longest path, right, for propagation delay. So this is the longest path, mentioning 5 nanoseconds, right? So for that circuitry we will take TPD as 5 nanoseconds, right? So let's talk about TCD, right? So here we have 2, 1, right, and here we have 1, right, and 1, right? So in case of TCD, right, so what we can do, right? So you can see that in case of TCD we have 1 plus 1, right? If I talk about this part, right? So again here if I draw, right, so this is one part and this is the second part, right? So for this 2 plus 1, right, this is 3, and this is 1 plus 1, 2, right? So this is TCD, right? TCD, contamination delay, right? So in case of TCD we will be having, we have to take the shortest path. So this is the shortest path, right? So you can see we have the, right? So that's how we handle, right? So after having few examples from combinational logic, let's talk about the timing parameters and timing analysis if we have the sequential logic, right? So you know that when we talk about the sequential logic, we have different building blocks, and those building blocks, they include flip-flops, right? And those flip-flops, they are clocked, right? So and we have to do some additional things in order to evaluate the sequential logic, right? Clocked sequential logic, right? When we talk about the timing analysis, right? So flip-flops, in case of flip-flops, right, they change value, right, whenever we have change in the clock input, right? So here how the flip-flops, they can be positive edge triggered or negative edge triggered, right? We can have both sort of flip-flops, right? So in case of sequential logic, how we define the propagation delay, right? So that indicates the amount of time required for a change in the flip-flop clock input, right? For example, if you have the rising edge, right, so you will focus on rising edge, and on the other hand, if we have the falling edge, so we will be concentrating on falling edge. So whenever we have a change in the clock, and then there should be a change in the output, right? So the time the clock is changed, right, and after the change of the clock, the output has to be changed, so there is no instantaneous change, there is a delay, right? So that delay is normally called the propagation delay in case of the flip-flop, right? So in case of sequential logic, we also define contaminational delay, right? So that indicates the amount of time required for a change in the flip-flop clock input that result in the initial change in the flip-flop, right? So whenever we have a change in the clock input, right, and the output start changing, right, so that is the same case, right? So we will be having the timing diagrams, right? So here we have the D flip-flop, right? So we all know the truth table of D flip-flop, right? Q follows D, so this is Q, D, and this is the clock, right? So there is no bubble, so it means this is active high or positive edge triggered flip-flop, right? So this is the input, right? So you can see that we have both sort of possibilities, and this is the clock, right? So this is the clock and this is the Q, right? So here you can see that on the positive edge of the clock, input has to be changed, output has to be changed, right? So there is no change, right, till TCD, right, contaminational delay, right? And whenever the input start changing, right, so it requires or it needs some time to attain the level, right? Or if it has to go to 0, so it needs some time, right? So here you can see that we have, if it has to go from 1 to 0, right, if we have Q has to be 0, right? So it needs this much amount of time in order to have 0, right? If it has to go high from 0 to 1, right, so it need this much amount of time. So here you can see that we have the propagation delay, right? And in that case, in case of the sequential logic, the propagation delay also includes TCD, that is the contaminational delay, right? So here we have defined propagation delay, right, and that indicates the amount of time required for a change in the clock input, right, and that clock input results in the change at the output, right? So here you can see that the clock have changed here, right, and we have the effect of clock change, right, here, right? So this is a sort of T, and we have mentioned this with TCLK dash Q, right? So, and this is TCD, right? So here again we have more detailed picture, right? So clock D, and this is the output, right? So here you can see that we have defined some other parameters, right, and these are the setup time, right? So you can see that that setup time indicated by TS, right, indicates the amount of time before the clock edge that data input must be stable, right? So the data must be present at the input, right, before this much amount of time, right, right? This much amount of time when the active clock edge arrive, right? So we have to make sure that that data is present at the input of the flip-flop before this much amount of time when the active clock edge arrives, right? So this is the hold time, right? So here you can see that the D should hold its value till that amount of time, right? So indicates the amount of time after the clock edge that data input must be stable. So it must be stable, or you can say that it should hold this input value, right? So that is D. So we introduced two new parameters, TS and TH, representing setup time and hold time respectively in case of sequential logic, right? So here we have the timing diagram, right? So you can see we have TS, this is the input D, right? And this is TH, this is the clock, right? So you can see that the input has to remain there till the right clock edge arrives, right? Before, so in other words, you can say, or in simple words, you can say that input should be present at D, right, in advance, right? How much time? TS time before the active clock edge arrives, right? So you have to first apply the input, right? And after TS time, the active clock edge arrives, and then your circuit will function properly. On the other side, right? So this clock edge has arrived, right? So after the arrival of the clock edge, the input must remain stable in that state till TH time, right? So here you can see this is the clock, right? So and this is the output, right? So these are the, you can say, two requirements or restrictions. We have to restrict ourselves to those requirements, right? So again, these are the explanations, right, mentioning hold time and the setup time, right? So whenever we talk about the combinational timing analysis, you can have an idea that we always talk about the input and the output, right? And there are some timing parameters that we define: propagation delay and the contamination delay, right? Whenever you talk about the sequential devices, clock sequential devices, right, the timing parameters for the clock, for those clock devices that constitute the sequential logic, they are specified or they are declared while taking into account the clock input, right? Active clock input. It can be a rising edge or the falling edge, right? So here we normally associate the timing parameters with the clock edge, right? So the setup time and the hold time, they are the restrictions, right? Or they are the must have parameters. If we will not obey those restrictions, right, so we will be violating and our design or our circuit will not function properly, right? So these are the limits, right? Okay, so here we have another example, right? So here you can see we have the D input, right? This is the clock, and you can see this is the macroscopic diagram, right, mentioning the setup time, right, and the hold time, right? So we have to make sure that input is present at D before, right, active clock edge arrives, right? So this is the setup time. You are setting up, you have to set up the device before this much amount of time, right? So after the clock edge pass away, right, so this is the rising edge and it is passed now, and after it's passing, right, you have to make sure that input is valid till th time, right? So whenever you talk about, or we will be analyzing the timings in case of sequential logic, we will be taking into account those different parameters. These are CD, right? Because you know that the sequential logic, it includes combinational logic, right? Whenever we talk about the output, we need the combinational logic, right, in order to have the output. And whenever we talk about the input at the flip-flop, right, so we have sometimes combinational circuitry at the input of the flip-flops, right? So you can see here we have the TCD, TPD, that part is combinational, right? And here we have the sequential, right? So now we will be having the timing analysis, right, of both our combinational and the sequential, right? So here we have a sequential circuit, right, the flip-flop, and this is the combinational circuit, right? So that in output goes into the combinational logic, and then that combinational logic produces some output that is input for this flip-flop, right? So we have mentioned different values over here. So this is TCLQ, right? So you can say this is the propagation delay for this flip-flop, right? And here we have two values, right? TCL 5 nanosecond and TS, right? So this is the setup time, and that is the setup time for this flip-flop FFB, right? So what we need to do, we need to calculate the minimum time between rising clock edges, right? So here we have to calculate the time, right? So this is the T minimum, right? And that will be T propagation delay of this, right? TPD G, right? So that is, we name this as G, and TS, right? Because here we have only one path from input to the output, right? So we will be having only one choice, right? So so we will be tracing the propagation delays from this to this, right? So you can add those values, right? So that will be 5 nanosecond, right, plus 5 nanosecond plus 5 nanosecond, right? So that will be, right, so T minimum will be equal to 15 nanoseconds, right? So F maximum will be, right, 1 over T minimum, right? So that is 1 over 15 nanoseconds, and you can calculate the, and you can also draw the waveform at your own, right? So here we have another example, right? So here we have more than one paths, right? So you can see that this is one path, and then we have another path like this, right? So let me draw. This is one path, right? And this is another path from here to here, right? Loop, you can say it, call it a loop, right? So what is the minimum clock period for this circuit, right? So what we need to do, we need to evaluate all flip-flop to flip-flop paths, right? So here are the calculations, right? So path from flip-flop A to flip-flop B, right? So this is the path from flip-flop A to flip-flop B, right? And that includes this combinational circuitry also, right? So what we need to do, this is the propagation delay for this flip-flop, right? So this is the propagation delay for this combination circuitry, plus we have to include TS, right? Because here we have the loop back, right? Or you can say we have a loop and we have a feedback, right? So this is a sort of feedback, so that's why we are including TS here, right? So this and this, right? So 5 nanosecond plus 5 nanosecond plus 2 nanoseconds, right? So there is another path from flip-flop B to B for this loop, right? So that is B. This is propagation delay for this, right? Combinational logic, that is F. Propagation delay for this, right? And plus setup time for this FFB, right? So here we have 4 nanosecond plus 4 nanosecond plus 5 plus 2, right? So you can compute. Okay, so let's talk about the hold time, right? So here we have the same circuitry, right? And this is TCD 1 nanosecond, TCD 2 nanosecond, and TH 2 nanosecond, right? So as we have mentioned that in case of the sequential logic, the input at the flip-flop, right, or at the sequential circuit should be valid till TH, that is the hold time, right? So on the other side, right, on the other side, contaminational delay, it normally ensures that the signal doesn't change, right? So here we have TCD plus TCD. This is for flip-flop A, right? This is for flip-flop for this combinational circuitry, right? So that is the hold time, right? So that is equal to 2 nanoseconds, right? So there is some relation between the contaminational delay and hold time, right? So here you can see that the hold time, we have already defined that the time that input should be stable or should remain there, right, after the arrival of the clock edge, active clock edge, right? On the other side, the contaminational delay, it restricts the circuitry, right, not to start changing until a predefined amount of time, right? So signal, it ensures that the change should not be occurring, right, even after the active clock edge, right? So we have to make sure that the TCD should be greater than TH, right? So here if you talk about this circuitry, you can see 1 second, right, and 2 seconds. So we have total TCD of 2 nanosecond, right? So that should be greater than this hold time, that is 2 nanosecond, right? So here again we have a more complicated circuitry, right? So here you can see we have the feedback, right, or loop. So path from flip-flop A to B, right? So here we have TCD, right? So this is 1, right, for this flip-flop, right? So again for this we have 2, right? So that the hold time should be as here, right? Contaminational delay should be greater than 2 nanosecond, right? So that we can meet the hold time, right? So here this is another path from flip-flop B to flip-flop B, right, for this loop, right? So you can see that we have for this 1 nanosecond, for this 1 nanosecond and for this 2 nanoseconds, right? So this is again 4 nanosecond, but we always take the shortest path, so this is the shortest path, right? So it means that the CD should be greater than 2 nanosecond, because 2 nanosecond is the whole time, right? So here how we determine the maximum clock frequency, right, in case of a sequential circuit, right? So we have an example over here, right? So you can see that we have both the sequential and the combination circuitry over here. So this is the path, right? So propagation delay for this flip-flop 10 nanosecond, 2 nanosecond, 2 nanosecond. This is CD, PD 5 nanosecond, right? So here we have a lot of different parameters that includes the setup time and the hold time, right? Because here we have the output, so that's why we have TS and TH over here, right? Right. So you can see that there are no bubbles involved at the clock input, so it means we have the rising clock edge, right? So this is valid, right? So here how we will be handling or calculating the T minimum, right? So this is the propagation delay for this flip-flop, right? So TPD for this inverter, and this is the setup time, right? So you have seen that we have included the setup time here, right? So 10 nanoseconds, right, 5 nanoseconds and plus 2 nanoseconds, right? That is a total of 17 nanoseconds, right? So how we have, so this is the T minimum, right? T minimum is equal to 17 nanoseconds, and we have the relationship of F max is equal to 1 over T min, right? So 1 over 17 nanoseconds, and that is equal to this figure, right? 58.8, right? So here again that is the timing diagram, right? So you can see this is the input D, and this is X, right? This X and this is Y, right? So you can see that and this is the clock, right? This is the propagation delay, right? And here we have the TPD, that is basically for this, right? This is the propagation delay for flip-flop, and this is the propagation delay for this combinational element, right? And this is the whole time, right? TS, right? Y will be should be present. This is the setup time TS, right? So Y should be present before this time, right? So this is the TS mentioning the setup time, right? So input must be present, right, before this much amount of time, right, when the clock, active clock edge arrives, right? So this is the TS, right, and this is the output, right? So we have calculated this 58.8 megahertz, right? So here we will be validating the whole time, right? So we have another example, right? So this is for the validation of whole time, right? So you can see that we have propagation delay, TCD, right? So this is the propagation delay and contamination delay for this inverter, right? So here we have the propagation delay, contamination delay, and this is setup time, and this is the whole time, right? So you can see that 2 nanosecond, right? So what we need to do, we need to calculate the TCD, right? So as we know that we will be looking for the shortest path whenever we talk about the TCD, right? So here you can see TCD 2 nanosecond and TCD 2 nanosecond, right? So we have 4 nanosecond, right? So the hold time should be less or equal to this contaminational delay, right? So where is the hold time, right? So this is 2 nanosecond, right? So it means this is a valid hold time, right? So if I talk about THB, right? So that is 2, right? So that holds, right? So that is less or equal to, right, the total contaminational delay, right? So here again we have to look for the valid hold time, right? So we have A, right? So here you can see that we have the block diagrams, right, rather than, so from those values we can recognize either it's combinational or the, or here we have mentioned the combinational logic, right? So from the values we can see this is the sequential flip-flop, TCD, contaminational, setup and hold time, right? So, and here again we have the clock Q, right? That is the propagation delay regarding the flip-flop, contaminational delay, right? Setup time and hold time, right? So here we have the combinational timing parameters TPD, propagation delay CD, right? So again this is the propagation delay and this is the contaminational delay and so on and so forth, right? So here you can see, right, we have to evaluate different paths, right, from A to B. So from this A to B, right? So 1 nanosecond and 2 nanosecond, right? So here we have 1 nanosecond and, right? So you can see that where is the, right? So you can see we have hold time 1 nanosecond and TCD that is 2 nanosecond, right? And from A to C, right, again A, hold time 1 nanosecond, and we have to look for the CD, right, from A to C. So from A to C we have, this is the shortest path, right, this is the longest path, right? So for shortest path I need to 2 plus 2, right, and then for B to C, right, so B to C you can see we have 2, right, plus 2, right? So again here it holds, right? So THB, right, THB, where is THB, right, is less or equal to TCD, right, A, right? If I talk about this, right, then this C is less or equal to A plus Z, right, A to C, from A to C, and then from B to C, right, from B to C you can see from B to C this, right? So all are the valid hold times, right? So whenever we talk about the sequential circuit timings, so they normally, the sequential circuit timing analysis, they it rely on the clock, right? So you can say because we need to look the data movement, right, from input to the output, right? And whenever we talk about the sequential circuitry, right, so clocked sequential circuitry, right, they rely on clock. Everything is carried down on the arrival of the active clock edge, either negative or positive, right? So the data movement is correlated with the clock, right? So we have to rely on clock signal. And you know that in case of sequential circuitry, we have both the combinational and the sequential components that are being involved, right? So whenever we talk about the sequential logic timing analysis, we have to take into account all the parameters that are involved uh, for combination circuitry and the sequential circuitry, right? So we need to take into account all those corresponding parameters, right? And on the basis of that analysis, right, we can calculate the maximum clock frequency, right, or the minimum clock timing, T minimum or F max, right? So what normally we do, we calculate or analyze, right, every path starting from one flip-flop to the other flip-flop, right? So that on the basis of that, we normally calculate the T min, right? And then we use the formula and we find out the F max, right? So these are the steps whenever we talk about the sequential circuit timing, right? So that's all for today's lecture, right? So today we have discussed the timing analysis. So we started from the combinational circuitry, right? And in the combinational circuitry, we discussed about propagation delay and the contaminational delay, right? And then we switched to the sequential logic, right? So as we know that the sequential logic, it involves combinational logic and the sequential logic, right? So we need to take into account all the parameters that are defined for combinational logic when we are analyzing the timings for the sequential circuitry, right? So we define some new parameters that includes the setup time and the hold time regarding the sequential logic, right? And then we have taken few examples where we calculated the time, right, T minimum, right, or you can say the minimum path, right? And then on the basis of that timing, we have calculated the frequency that is being used for this circuitry, right? So that's all for today's lecture. मेरी तरफ से अल्लाह हाफ़िज़, अस्सलाम वालेकुम.